All right, guys, welcome back after lunch to our paper reading session. We are going to do 3 papers. Last time, if you recall, what did we do last time? Anyone remembers? We did donut and the TROCR, right? So the topic, just to whet your recollection, is document AI. We are still on the topic of document AI, and we are going to do the remaining things today. Document AI is taking a document which may have text on it, and the definition of document is a little bit more general. Document could be, for example, text. It is basically text extraction process. So, for example, if you look at the word coffee is written here, right? Is written vertically, or if I take this paper, research paper, and I show it to you like this, to the camera like this, it is not, or especially like this, you realize that the text is not in a linear fashion. It is bent, it is skewed perspective, right? It is tilted. And so these are called scene text. The text that you see on billboards, the text that you see written on, for example, a soccer ball, right? Or things like that. The ability to extract text from scenes is part of, in some sense, part of document AI. Generally, when people talk document AI, they misconstrue that it means just scanning some paper, taking a scanned picture, and then extracting text from it. It's generally a little bit broader than that. So to emphasize the fact that you can get text in an image in a whole variety of formats, I'll pick up 2 papers. One of the paper is Text Snake, which will deliberately extract text written in very convoluted way. So imagine that there's a little helicopter flying or an aeroplane flying, and they often have advertisement banners. And the banners are flying in the air. Something is written on a flag. How would you read that? Right? How would you have an AI read that? So that is a challenging problem. And the interesting thing is people have worked out algorithms to take care of this. But today, I will go back to one of the original papers. Is that it? Yeah. Guys. Yeah. So we have the situation that we live in the world of transformers. Everything is done through transformers these days. So people have sort of forgotten that there was actually an era, prehistoric times in some sense, when we used to do most of our things without transformers. Now, jokes aside, even today, a lot of the work that we do can be done and is done in production without transformers. A lot of large-scale enterprises do billions of image processing actually without transformers. So what I will do in the first paper is go to one of the original papers for text extraction that did it. This paper is 2015. And what this paper did is ask if something is written on a document, let's say that you have writing on a document, how can you extract a text from it? And if you look at the world before transformers, go back to 2015, what was happening in 2015? Deep neural networks were there, right? And there were a few successful architectures dealing with images. For image classification and image segmentation, which particular neural architecture was the best? Anyone recalls? Convolutional neural networks, right? You would do a convolution. What is a convolution? You have a picture and you look at a region, local region, and you extract the information not from a pixel, but from a local region. Right? The filter would convolute over the image and you would do local feature extractions. Right? So we had, for images, the state of the art was convolution, neural nets. Now, when it came to text, generating text, the state of the art in those days used to be, if you remember, before transformers, were all RNN, recurrent neural network. Let me put the whole word here. Recurrent neural nets, right? And their cousins like LSTM, GRU. Even though GRU is of a more recent vintage, but think LSTM, right? Most of the if you thought about autoregressive, what do I mean by autoregressive? Abhijit? What is autoregressive?
When you take the output into the input.
Yeah, it regresses on itself. In other words, it's based on what it has produced so far.
Feedback.
Partly feedbacks. Like, for example, the next word that I will say depends not only broadly on what I have to say, but also on the words that I have said so far, right? Because it's a continuation of a sentence. So that those models are autoregressive models. So text generation is an autoregressive. Now, but classifying an image generally is not autoregressive. And why is that, Sanjay? That's why I called out. Okay, anyone, why, when we look at an image with a convolution, why is it not an autoregressive thing? There is no autoregression here.
Why CNN is CNN network is like a layered network, right? One different dimensions are feeding the other layer.
That is true. Okay, that's one way of putting it. Patrick?
Yes, because each layer is particular to the part of the convolution.
Yeah, there is no sequence here.
There's no feedback.
Right? So there has to be a temporal sense before you talk of auto-regressive. It's just an image. You say it's a cat or a dog, or what do you see in the image? You segment it in by saying there's a house, there is a road, there's a car, there's a pedestrian, right? So, but there's no sequence here. So there were two fundamentally different worlds. The world of images, where you would look for mask and segmentation or recognize and classify. There, if you remember, this is 2015. Right in 2014, ResNet had come out, BGG, etc., were on the horizon, and they were crushing the benchmarks. In those days, the benchmark was MNIST, right, and ImageNet, and so forth. And those convolutional networks were doing extremely well. The use of GPUs, right, was just beginning to take off because you could do massive parallelization. And yet, when you look at it, the document recognition, people would broadly use the term OCR, it was doing pretty poorly. It wasn't doing as well. And so it was natural to ask, can we apply convolutional networks to the document AI problem, right? And in particular, in those days, it was like a optical character recognition. So when you do that process, optical character recognition, actually there are two problems that you solve. One is the bounding box problem, the segmentation problem. Where is the text, right? You need a bounding box on the text. And once you have a bounding box on the text, then you ask the problem of recognition. So one is of detection, one is of recognition, and then you get what you want, right? So that's how people used to look at it. So the first use was pure convolutional network. They said, hey, how hard can it be? Let me go over it and recognize this was a A, this was a B, and so on and so forth. And we will try to somehow recognize the text. Those approaches sort of worked, but not as well, till this paper came out. And it was one of the papers, I suppose there were a few similar papers that came out, but I took this one because it has a lot of references and was heavily quoted if you look at arXiv. So what it said is, let's do one thing. Let the CNNs do what CNNs do. What do? They do feature extraction. They convolute and they create a channel. So when you take 10 filters over an image and run over it, what do you end up creating? You create 10 sort of feature maps, isn't it? 10 different feature maps out of that image. And each filter is looking at the image in a different way, right? And now you ask this question that if we treat these feature maps and forget about the feed-forward network at the end to linearize it because you're not doing classification, you take this and then you ask this question. Suppose I take this feature maps and somehow can feed it into our LSTM, into a recurrent neural network, or LSTM is the most popular variant into that, because it is autoregressive. So let it treat this input, come up with a hidden representation, and then start emitting what text it could be. And you realize that suppose I have a letter, let's say that I have something like this, right? This could be a T, right? But suppose I write it or F or God knows what. But the moment I write it like this, now it begins to look most likely to be what? A J, isn't it? Even though it doesn't look like a J, but it is somebody's interpretation of a J or writing of a J. In other words, they recognize the fact that the accuracy of the next word that you recognize depends on the words that you have recognized before. So the autoregressive aspect plays in your favor. It reinforces the predictive power or accuracy of your model. So for that, you somehow need to hybridize it with a LSTM, with a recurrent network. And so the core idea of this paper, and this was 2015, when it came out, it went through widespread adoption, this sort of ideas. So what they do is, let's take the picture of a cat, right? How does a cat look like? Here's a cat, right? And so what you start doing is you start creating lots of channels out of the cat by convoluting over it. You create a feature map. And of course, you go through many, many layers. You may convolate, do your max pooling or average pooling, whatever it is. Actually, in those days, in 2015, average pooling was much more favored than max pooling is. Max pooling tends to be a more favored, max min pooling based on whether it's a dark or light image. So you do this, you convolate again, you do this. Ultimately, what you will end up with is lots of feature maps. Right? Let's take an arbitrary number. Let's say that you end up with 64 feature maps. Right? Because the layer just before it, you put 64 filters in front of it. Are we together? Though the number may be much more, actually, maybe 512. These days, 64 is considered too little. You can go much higher. You have these things. The whole question is, if I want to feed it into, now what do I need to do? I know that somehow this contains the information about the cat. It has done the feature extraction. The trouble is, the RNNs, they are looking for tokens, right? Vectors, a sequence of vectors, isn't it? LSTMs are looking for a sequence of vectors, but these are feature maps. How do I create a vector out of it? That's a bit of a problem. So what they do is, so let's take this feature map A, B, C, D, E. Let me just take 5, even though there are lots of them. You take it, A, B, C, all the way to E. And what they do, and it's a clever technique, they said, what if we did this? Take vertical column. If you think about the vertical column here, it must be about the first layer's interpretation of this side of the cat image, isn't it? Then I take the vertical map from each of these layers. So each of these feature maps is reinterpreting that vertical slice of the cat in a different way. One is maybe focusing more on the color, one is focusing on the edges, or whatever it is. I mean, those are not exactly correct ways of saying it, but think of it. Each feature map has some information about the image. And if you train the network well, they will not have overlapping information, but have different orthogonal information, right? So that the information content is maximized. So each of these A, B, C, D, E have understood that part of the cat image in a different way. And so you bring in the next one, let's say this guy. And so you focus on this vector. So now you have a green vector. And what you do is, by the way, the A orange, you concatenate all of these. Like you take this. Actually, I should use orange. Orange. So you do this. You take this together with this together with this together. So what do? These are vectors. These are column vectors, isn't it? If these are numbers, you realize that so far you're looking at a column of numbers in the feature map, isn't it? Because a feature map is a grid of numbers. What kind of numbers? Floating point numbers, right? They have the RGB channel, but they are numbers. Now, if I take this particular column, let's say that this is by the time you reach here, you're looking at 16 by 16. I'll take an example. So what do you do? From A, when you pick the orange column, you get a vector of length 16. Does that make sense? You get a vector of length 16. Then you concatenate the B vector, the B orange vector, and the C orange vector, and D and E. So you end up with 5 of the 16 segments. And so you end up with a vector of length 80, let's say. Are we together? In the language, now take it this way. So you will end up with a vector that is basically, hang on, let me just see. One is you will have a green vector, you will have, which comes from the concatenation of all the features. You will have a orange vector. You will have, let's take another color, blue. Third is blue. So you would agree that you will end up with blue here and so forth, right? Are you getting that? And now think about RNNs, recurrent networks, sequence to sequence models. Do you realize that this now is your classic sequence? This is a sequence. What you have ended up doing is you have ended up creating a sequence of tokens. It just so happens that those tokens were derived not from words, but they were derived from images. But as far as the LSTM is concerned, would it even know? It would have no clue. What will a LSTM do? As far as what is the basics of a sequence to sequence model? You have an encoder and you have a decoder, right? And then LSTM is just smart. It has a forgetting channel and a memory channel and so on and so forth. But let's not get into the details of LSTM. If I feed this sequence into it, what happens? You will end up with a latent representation, a hidden state. It will end up with a hidden state of this sequence. Are we together? Right? So think you're translating English to French, the classic sequence to sequence model, right? Isn't it very similar? You're converting from a visual language tokens to a textual language token, right? And so you want to decode it as, let's say, English text. Make sense, guys? And so what it will do is you feed this into a LSTM, which was the state of the art in RNNs. And what you will end up with is some sort of words. But there is a catch to it. If a word is really fat, then it may take, so for example, let us say that the word written was A. Now there is a problem. The word A is actually captured by not one token, but it takes a few tokens to capture it, isn't it? But that works completely in our favor because this goes into the hidden state, and from the hidden state, the decoding is just like what happens. Sometimes you have 2-3 words and the meaning becomes clear only when you put the words together. For example, bench by the bay. Together they form a concrete meaning, isn't it? Something like that. So it works in our favor. The other advantages of this encoder decoder model, which is much better than what people were doing just with CNN, is they had no idea what is the length of the text. And they had this big problem unsolved. But here, what is the property of autoregressive models? The length of the output is arbitrary. It will keep producing output till it happens to produce a special token, predict a special token, and that token is what? Stop or done. The moment it happens to say, oops, the most probable token is done, then it will stop. But till then, you don't know how many tokens it produces. Are we making sense, guys? Right? And now comes and this is the beauty of it. But what happens is it ends up producing, and I want you folks to pay attention. I'll just zoom. Oh, touch is on. Look at this. Are we looking at this image, guys? And do you notice that this word state at an angle goes through, becomes all these feature maps from this? Do you notice that column by column, you're extracting the vectors, the so-called tokens to be fed into the LSTM, right? You feed it into the LSTM. Now observe the word deep bidirectional LSTM. Why is that? The interesting thing is when you're trying to predict what word it is, the word state, it helps not just to look from left to right, but you can also look right to left. So for example, suppose you were unsure. So let's think of it this way. Suppose you had this much stat. Now, what are the most probable characters after that? E, S. If it was S, it would be stats E. But the unlikely is Z or B, isn't it? So how do you know what is more likely? Well, there are two ways of doing it. You can look up it's called a lexicon. So in this world, we look at there are two in those days, and even today, we use words like lexicon based and lexicon free. These are two different approaches. So what is lexicon based? You have a finite dictionary of words, lexicon, and you say, hey, in my lexicon, the words are stats and state, and maybe statistic, so TI, but I don't see STATB, so a lot of them are ruled out, isn't it? So I have to pick only from this. It helps you. The other is a lexicon free just says that, I don't know, just as a pure recurrent network, tell me what it should be, what it could be. Right? So when you do this, because you can have half a word and things like that, you will end up with something like this. Right? Now, can you see where this corresponds to? You see that empty space there, right? It also has latched on to a little bit of empty space, perhaps. There. Right? So it is picking up, and after that, again, you see there's an empty box here, right? So it's a problem, and they must have noticed that they were getting something like that. It was a very noisy inference, right? When you do inference like this, just using a LSTM, and you can do backward and forward, by the way. So for example, if backward is important because it gives you confidence in S. Suppose you knew that Tate is here. What character would you like to place before it? S looks far more likely, isn't it? So it helps to do bidirectional LSTM. That is why they call it deep bidirectional network, because what they do is they stack a few LSTMs one on top of the other. In output of one goes into the other, right? And then they end up with this. And then they say, you know what? This is still noisy. What can we do with it? We can then feed it into another machine, a transcription machine layer, right? In here, we can put in another recurrent network, because we can treat it as another translation or sequence to sequence model, isn't it? That noisy data is almost like, think of it as almost like a different language goes in, and you have to translate it and pick words only in a clean, much cleaner, simpler language, right? And so you can now the reason this is interesting is, see, in one shot, a picture is going in, becoming features, becoming tokens, going through LSTM, and going through finally the transcription layer and going here. You're doing it at one shot, like successively, staggered it. What is it? You notice that at each point, because they are all connected by a pipe, if there's a forward direction, there is also a backward direction. What can I do for backward? What can I use the backward information propagation for? I can do the loss, right? So suppose my data in a supervised learning is, somebody has said that this word was state, right? And it produces state, then I have no loss. But suppose it produces some other word, abate. Oh, sorry. In this very high resolution, it's looking pretty bad. Abate. Suppose it infers the word abate. I'm just taking an example. Now what can you do? You can create a loss. Now the question is, from the loss, who can learn from the loss? From the back propagation of the loss, who can learn? And you realize that everything can learn. Not only these LSTM layers can learn, but even these, the CNN can learn. It can produce better feature maps such that this mistake doesn't happen. Are we making sense, guys? Yeah, that is it. So the strength of this algo was that because you do it as one single pipeline, when you back propagate the loss, you can back propagate it all the way through two different neural architectures, through LSTM layers and through convolutional layers. And both of them co-learn at the same time. Beautifully argued, right? It's a beautiful paper. And in those days, it was quite a remarkable paper, right? So now look at this figure. It says the network architecture consists of three parts: the convolutional layer, which extracts a feature sequence from the input image, of course; recurrent layers, which predict a label distribution for each frame. Simply put, it predicts what character it will be. And the transcription layer, assuming that what it produced was noisy, a transcription that will clean it out layer, which translates. So the second and the third are recurrence.
Isn't it bigger bang for the buck for the second and the third? I'm still kind of debating the feature map and whether there is a real value in doing that.
No, because recurrence cannot recognize anything in a picture. No? Oh yeah. Simply put, you need a theory. Okay. Right. Okay. So I need to become good at gestures on this one. Okay, there we go. My fingers work. So this is it. At the end of it, now, so this is the whole of this paper, guys. Now, let us read it a little bit more carefully and we'll move on to the next one. I'll just stick to the abstract. Image-based sequence recognition has been a long-standing research topic in computer vision. Yes. In fact, it predates deep learning and all of that. People have wanted to do it for a long time. In this paper, we investigate the problem of scene text recognition. Give me 1 second. I think we have run out of battery. Scene text recognition, which is amongst the most important and challenging tasks in image-based sequence recognition. A novel neural network architecture which integrates feature extraction, sequence modeling, and transcription into a unified framework is proposed. Right? Compared with previous systems for scene text extraction, the word scene text represents the fact that it's a generalization of a document. Right? It could be anything. It could be the side of a Coca-Cola bottle. Right? Compared with previous systems for scene text recognition, the proposed architecture possesses 4 distinctive properties. It is end-to-end trainable. Do we see why? Right? It can. There is no break in continuity. The signal is propagated forward. Each stage remains differentiable. And because it is a differentiable thing, you can back propagate the gradients. And so you can do a continuous learning all the way. Right? It is end-to-end trainable in contrast to most of the existing algorithms whose components are separately trained and tuned. Right? Second was, it naturally handles sequence in arbitrary lengths, involving no character segmentation or horizontal scale normalization. So people were doing all sorts of hacks. They were trying to make it into a box, size box, and say, now I can recognize. You can't do that. Now, where do we get this property that we can produce text of arbitrary length? Because of the RNNs, right? You don't know. Yeah. Because of the RNNs. It naturally handles sequences in arbitrary length. That is it. And the third point is, it is not confined to any predefined lexicon and achieves remarkable performance in both lexicon-free and lexicon-based scene text recognition tasks. Which means that, see, you can choose to, once you reach this stage, you already have a recognition. Suppose the word state or is not there in your lexicon. That's perfectly fine. It will still produce the word state if any of the probable words are not so likely. Right? So you can do a lexicon-free generation also, which is the thing. And then the next point it makes out is, it generates an effective yet much smaller model, which is true. What people were doing is they were hacking by putting lots of models in a pipeline, right? And guys, do you notice that this whole thing keeps going on? We have certain amount of technology, like today, right? What are we doing? You guys made your enterprise pipeline. So many pieces are there in the pipeline, right? And then comes a research paper that says, this is all you need, right? And then it just squashes everything together. Right, simplifies everything. So in some sense, you have that. It's basically saying it's a much simpler model. One single model does it all, right? So, which is more practical for real-world application scenarios. So this word I would like to emphasize. It is more practical for real-world application scenarios. That is true even today. Today is 2023, and this has been there for 8-9 years now. This thing remains an industry workhorse, right? One of the leading industry workhorse, even though transformers have come. In fact, it is far cheaper to work with this than with, as you can imagine, transformers, right? So it has remained. So this is it. Then benchmarks say it is better and so on and so forth. We can go into the proposed network, feature sequence extraction. This is the main thing that I explained to you about how to pick the column vectors is given here. Oh, sorry. Specifically, so this part would be hard to understand. Specifically, each feature vector of a feature sequence is generated from left to right, given an image, just as we did. Did we do left to right? Do you notice that we started with orange, then green, then blue? Left to right on the feature map by column. Did we pick the columns? Why? Because if you pick the column, you keep the locality, local visual information together, right? You're basically, to use a very gory metaphor, slicing the cat vertically, right? So don't do that. This means Go ahead.
You said that this is scene text, right?
Yeah.
Suppose that I had a picture where, like a billboard or something, where the text goes, say, from top to down, right?
Yeah.
Sometimes you have these large signs or something like that. Then this model probably is not going to work there, correct?
Exactly. So you just identified a crucial condition where this wouldn't do so well. So then it would need pre-processing steps to rotate the image and so on and so forth. Right?
But then how does the thing on, like you mentioned, that the Coke cans and all of those stuff, where they may be in the same direction but may not be completely horizontal, right? They might be at
Absolutely.
an angle or something, right?
So those are the limitations of this architecture. Sachin, you identified it right. Those are the limitations, which is a good segue into our next paper. Right? So we are coming to that. So guys, the rest of it is straightforward sequence labeling, lexicon based transcription. What is a lexicon? Lexicon is a vocabulary. It's another word for vocabulary. If you know that you must predict the word from within the vocabulary, the only question you ask is that what's the conditional probability? Which lexicon item or member is most probable given this output? Right? So that's that. Yeah. So this is your conditional probability at large. And then there is a lexicon free way also of doing it, which just says, tell me the probability. What is it? We don't care what it is. Pi, anything. It could be. Okay. So experimentally, as you can imagine, it has done very, very well in benchmarks of those days. And obviously, don't judge it by today's, but when you look at it there, you realize that given the benchmarks of those days, it is achieving state-of-the-art performance. Not always. Some places it misses, but generally it achieves state-of-the-art performance, right, with a much simpler architecture. Right? That's that paper. So I will end this one here, and we will go to the next thing that Sachin, you asked, which was what happens if the text is not linear, vertical, or in some other orientation, and so forth. So the other thing is you can sort of pre-process and change the orientation, but how do you do if the text is all windy and so on and so forth? So we'll do that. For us to do that, before I do that, I notice that some of you want a break. We'll take an exact 5 minutes break.
Asif, another little bit of information. That one of the other authors, right? He's most likely the professor, right? I may not be saying the second author, Jiang Bai.
Yeah.
I think. So his very recent paper is actually pose attention transfer. So given a stick figure, you can generate images of people with that particular pose. So where you can, so 2021. So he went from this understanding text into generating images of people and things like that for clothing lines and also that's the kind of area that he has moved into afterwards.
Yeah, amazing. Actually, share that paper. I'd like